What are acids? What are bases? I think you are familiar with the definition. Acids are solutions with pH values less than 7, while bases are solutions with pH values greater than 7. Or you also might be familiar with the definition that an acid is a proton donor and a base is a proton acceptor. But these definitions are very limiting and they can only explain a few select types of reactions. So let's extend your knowledge of acids and bases. In this lesson, you will learn about another theory that defines acids and bases. And this is what we call your Lewis theory. The Lewis theory of acids and bases was built on the idea that the presence of protons is not exactly the condition that must be met for you to have an acid and a base. Rather, it's the presence of a pair of electrons. Lone pair of electrons. That is important for you to have an acid and a base. So let's review. In the Bronsted-Lowry theory of acids and bases, you know that you have an acid if it donates a proton, such as what is being shown in this animation. You have 4 water molecules passing on a proton, one to the other. So you have an acid that passes a proton, and you have a base that receives the proton. So again, um, in the base, the H2O molecule that receives the proton, we see that the important part of this water molecule is the lone pair of electrons, because that will create the bond to which your proton, your incoming proton, will attach. On the other hand, your proton, a positively charged species which has a very high electron density, or sorry, very high charge density, 6 negative charge, right? It's very positive. So the proton, a very small ion, it has a positive 1 charge. Yes, the charge is small, it's just positive 1, but it is a very small species. So the charge density is very high. So it tends to seek a negative center, a negatively charged center. And that is represented by the lone pair of electron on your water molecule. So again, maybe proton donation and proton accepting is not exactly what we are looking for in order to define an acid or a base. Maybe it's the presence of lone pair of electrons. And this is actually what was called back then as the electronic theory of acids and bases. And it was just later on came to be known as the Lewis theory. This was presented, it was organized actually by Gilbert Lewis in the 1920s. So a lot of people contributed to the theory. Now, under this theory, again, we define a Lewis acid as an electron pair acceptor, and we define a Lewis base as an electron pair donor. So, what are Lewis acids? These can be molecules that have fewer than 8 electrons on the central atom. So, those molecules that we find as exceptions to the octet rule. They can also be ions that have a positive charge, such as your proton, and your transition metals, positively charged transition metals. And they can also be molecules in which the central atom can add additional pairs of electrons, even though it already has an octet or more of electrons. So these are also listed as exceptions to the octet rule. Examples are your tin, phosphorus, and sulfur central atoms, because these atoms can use their d orbitals to accommodate more electrons, more than the required octet. Meanwhile, your Lewis bases, they can be anions that have an unshared pair of electrons, like your hydroxide ion, hydride ion, fluoride, and phosphate ions. Or they can be neutral molecules, but they possess unshared or lone pairs of electrons, such as ammonia, water, and others. So we notice that this Lewis theory of acids and bases covers a wider range of acids and bases. So notice your positively charged transition metals, or your cations from the transition metal series, they are considered acids under the Lewis acid base theory. And even neutral molecules such as your boron trichloride or your phosphorus pentachloride, these are Lewis acids. Here are some examples of Lewis acid base reactions. So, for example, we have this is antimony pentafluoride plus a fluoride ion, and you form an anion which has a negative one charge. So, you have antimony hexafluoride ion. It is important to again emphasize that, so if we have our Lewis acid, so this central atom has um, it's not positively charged, but it has empty orbitals that can accommodate a pair of electron from the Lewis base, which is the fluoride ion. So the thing is, the pair of electrons that will be used to create the bond between the Lewis acid and the Lewis base, or the two electrons used to create this covalent bond, comes from only one species, which is your Lewis base, right? So two electrons will be given by fluoride ion to form the covalent bond. So for this one, we have a specific name. So it's called a coordinate covalent bond. Coordinate covalent bond. So again, in a coordinate covalent bond, the two electrons used to create the chemical bond or the covalent bond comes from one species. So it's different from what we learned in general chemistry, wherein, for example, you have hydrogen with one electron and you have fluorine, which has seven electrons. And what they will do is that they will share. So hydrogen will contribute one electron and fluorine will contribute one electron to form the covalent bond. So this is different. This is purely covalent bond, but this one is a coordinate covalent bond. Other examples, so you have here aluminum chloride plus trialkyl amine forming this adduct. You have hydrogen ion plus phosphorus trihydride forming phosphorus tetrahydride ion, chromium 3 ion plus 6 molecules of ammonia forming hexaamine chromium 3 ion. So notice the name is different, right? So you will learn about this nomenclature when you study coordination compounds. So again, we see that with the Lewis acid-base theory, we can explain a wider range of reactions compared to your Arrhenius theory, which was very limited, and to your Bronsted-Lowry theory of acids and bases. Now, there are some similarities that we can observe between the Bronsted-Lowry theory and the Lewis theory. First is that you cannot have an acid without a base. So in the Bronsted-Lowry theory, you have what you call the conjugate acid-base pairs, right? In the same manner, in the Lewis theory, you cannot have or you cannot define one as an acid without another species being a base. So the existence of one is important for you to define that this one is a Lewis acid or a Lewis base. However, in the Lewis theory, we don't call them conjugate acid base pairs. That term is only used in the Bronsted-Lowry theory. Next, an acid, or it can be a base, reacts to displace a weaker acid or a base from a compound. And you have seen this also in the Bronsted-Lowry theory. And the interaction of a Lewis acid and a Lewis base is also a type of neutralization reaction because the acidic and basic characters of the reactants are removed once they react with each other. So, a case in point highlighting this second similarity. So, for example, you know that boron can accommodate a maximum of 6 electrons. So, it's an exception to the octet rule. So, it has an empty p orbital, 2p orbital. Therefore, ammonia with a lone pair of electron can form a coordinate covalent bond with BF3 or boron trifluoride, and it forms this adduct. Now, if this adduct of ammonia and boron trifluoride is or if boron trichloride is added to a solution containing this adduct, what you will observe is that the boron trifluoride is replaced by the boron trichloride. So just like in your Bronsted-Lowry theory, the forward direction of this reaction is more favored than the backward because BCl3 is actually a stronger Lewis acid than your BF3. That's why it can displace BF3 from the adduct. So the question is, why is BCl3 a stronger acid than BF3? You might think that if we consider the structure of BF3, you have your fluorine atoms, which are the most, fluorine is the most electronegative element, right? So you might think that the fluorine atoms, since they are electronegative, they will tend to pull the electrons towards them, making your boron, your central boron atom, more electron deficient. However, that is not the case. So what's actually happening is that your boron again has an empty 2p orbital. Meanwhile, the 2p orbitals of your fluorine atoms are occupied by electrons. Now, by symmetry, the electrons from your 2p fluorine or from the 2p orbitals of your fluorine, so these three, they can actually delocalize, and this delocalization will involve um, the empty p orbital of your central boron atom. And this actually creates a resonance structure for BF3. So the bonds there have a double bond character, and so they're not purely single bonds. And again, it's because of the delocalization of the electrons from the 2p orbital of your fluorine atoms, thus actually making the central boron atom less electron deficient. Less electron deficient. Now, looking at your BCl3 has an additional shell, right? So the outermost electrons are already in the 3p orbital. Now, due to symmetry, the 3p orbitals are bigger than the 2p orbital of your boron, and this makes the resonance less favorable than the resonance in BF3. That is why your central boron atom in BCl3 is more electron deficient than the central boron atom in BF3. And this explains why BCl3 can displace BF3 in this adduct. Another question that we can ask regarding this case in point is, how does this type of reaction takes place? Actually, it's the same as your SN1, SN2 mechanism in organic chemistry. Okay, so It's possible that your BF3 leaves the adduct first before your BCl3 can form the coordinate covalent bond with the ammonia, with the free ammonia molecule. Or it's possible that your BCl3 forming the coordinate covalent bond is synchronous with the leaving of your BF3. Okay, yeah, so that also happens in inorganic molecules, not just in organic molecules. So for the next part of the video, we will now go to an extension, another extension of the Lewis theory, which is called the hard strong acid base theory or the HSAB theory.